Nature is benign, merciful, and awe-inspiring at the same time. Ocean is a prime element of nature we envision. Though bountiful, it often turns ominous for no apparent reason. While opening up vistas of immense scope in exploration and sustainable utilization of marine resources, coastal population bears the brunt when cyclones, tempests, and enigmatic tsunamis unleash their might. Aghast at the cycles of devastation and misery, humans can do little to overcome or contain their fury. Use of technology, nevertheless, facilitates in monitoring and forewarning the impending disasters. While weather observatories end at the edge where the land meets the sea, Ocean Observation System (OOS) of NIOT goes far beyond with its observational capabilities using the moored buoys. Principally, OOS designs, develops, operates and maintains moored buoy networks in Indian waters. Systematic collection of real-time meteorological, oceanographic and seawater level data is the prime objective of such exploits. This enhances the predictive capability of coastal and natural disasters, as well as short and long-term climate vagaries. There are three categories of moored buoys: Met-Ocean, Omni and Tsunami buoys. Met-Ocean buoys measure air pressure, air temperature, wind-cum-ocean current speed and direction, sea surface temperature, conductivity and wave. In addition to these parameters, Omni buoys measure solar radiation, rainfall, subsurface pressure, temperature, current profile up to 100 meters depth and conductivity up to 500 meters below sea surface. They are also equipped with global positioning system, beacon light, radar reflector and satellite transceiver. Sophisticated data acquisition units in these buoys process and store the data measured by the sensors. The primary source for power is solar energy. While irradiation actuates the systems through solar panels directly during daytime, energy is also stored in chargeable batteries for use in the night. Primary batteries, too, are employed as standby, augmenting the endurance of these autonomous buoys at sea. The Tsunami buoy system has two units, a surface buoy and a bottom pressure recorder BPR at seabed. Positioned nearby tsunamigenic vicinities, the BPR is capable of accurate detection of atypical real-time wave swings in the open ocean. Intercommunication between BPR and the surface buoy is established through acoustic modems. In the event of any seismicity capable of inciting a tsunami, the BPR measures the water column pressure and communicates to reception systems. The data captured by all these buoys are transmitted through satellite, along with location coordinates to the Mission Control Center manned 24/7 at NIOT Chennai. Consequently, simultaneous real-time data is disseminated to Indian National Center for Ocean Information Services, INCOIS, Hyderabad. Coastal buoys, a modified version of Met-Ocean buoys, have also been established by OOS in the coastal waters of India. They use GPRS and INSAT telemetry for communication. The Kalval buoy, positioned off Kavaratti in Lakshadweep Island in collaboration with Space Application Center Ahmedabad, serve as a validating platform for satellite observations. The coastal buoy deployed at Andaman Island plays a vital role in coral reef studies. In addition, the buoys deployed in Andaman and Lakshadweep serve as reference platform to test and calibrate sensors. Spurred by the complexity of weather forecast, auxiliary monitoring of parameters within and above the ocean's surface has become critical. Buoys in high seas alone can serve this purpose. The task of deploying the buoys, weighing more than a ton, is extremely laborious. OOS is fortunate to have an exceptional team of professionals to manage this. Distinct components of the buoy are brought on board and assembled. Sensors get tested for operational efficacy prior to and post-fitting. Next, the mooring systems comprising of combination wire rope, nylon and polypropylene ropes, along with floats and sinker weight, is prepared, specific to the deployment site, and connected to the buoy system, which imparts stability to the whole unit, which is exposed to intense currents, tides and gales. Subsequently, the vital satellite link between the buoy and Mission Control Center is launched. Real-time performance of sensors tested, quality of transmission ascertained, and response to commands from the control center established. The functional buoy system is then lowered from the deck, followed by paying off the mooring ropes and dropping of sinker weight to water depths ranging from 20 to 4,500 meters at the chosen locations. The challenge is often accomplished by working round the clock, unmindful of the rough sea or inhospitable weather, to keep pace with the scarce ship time. Periodical maintenance by dedicated cruisers is yet another daunting, repetitive errand imposed on the Team OOS, ensuring preparedness of the utility to the nation at all times. Team OOS also has forayed into innovations like wind-powered green buoy system, indigenous data acquisition system IDAS, dual communication system through INSAT and IMARSAT for tsunami buoys, Ardarsh, indigenized omnibuoy Prakruti, new generation buoy Sagar Bhumi, Aquabot, variable buoyancy of aquatic glider and advanced data reception and analysis system Address. Offshore is well known for its abundance of wind. After a pilot study, a wind turbine was installed on a buoy system to generate power required to charge its secondary batteries. The indigenous data acquisition system has repressed technology dependency and proven to be cost competitive. 6 variants of IDAS conceived, designed and devised by OOS such as MetOcean, Omni, Wave, Tsunami, INSAT and GPRS are developed by the industry and presently in operational mode. Development of a low-power system for these variants is underway. The laboratory-scale model of Aquabot is developed and field trials are going on. Variable buoyancy module attempts to control the buoyancy of aquatic gliders using dual buoyancy reservoirs. Hydrodynamic characteristics of the module are being studied and theoretical experiments revealed reduction in space and energy consumption. The structural parts and components designed would be validated using computational analysis. OOS is now poised for a big leap of technological breakthrough of visual observation around the coastal buoys from the shores far away. 3 high-resolution video cameras installed on the mast of the buoy system at 120 degrees displacement, capturing real-time day and night video and still images surrounding the buoy system, are transmitted through 3G telemetry. The buoys are also equipped with automatic identification system, the device capable of gathering useful research and surveillance intelligence on ships in the vicinity. The intractable terrains of the North Pole are legendary. The OOS-NCAOR team has achieved a milestone in the annals of ocean research on 23 July 2014. Fighting the odds of sub-zero temperatures and Arctic storms, the team became successful in establishing INDARC, the first Indian underwater moored observatory in polar waters. INDARC at Kongsfjorden, just 1,000 kilometers away from the North Pole Basin, holds a suite of oceanographic sensors for measurement of temperature, salinity, current profiles, and other vital parameters. The data obtained by INDARC would add impetus to the research on cause, impact, and effect of climate variability from a regional to global perspective. The untiring efforts of OOS has paved way to scale up the collaborative technical focus with international agencies like NDBC, NOAA, PMEL USA, and reputed organizations which include Scripps, JCOM, Jamstack, and multinational universities. Standard operating procedures of OOS are vetted by these reputed organizations and well appreciated for the OOS to be acknowledged at par with reputed buoy operators across the globe. The achievement, though substantial, is just a preliminary step in the long march of the nation's ocean observational needs.